Hey, hello, good morning, good afternoon, good evening, wherever time it is. So today we're going to start chapter 2. Our first objective is we want to be able to find and interpret the percentile of an individual value within a distribution of data. So the first thing we need to do is talk about what a percentile is. A percentile is the percentile of a distribution is the value with p% of the observations less than it. Okay, the best example is when you go to the pediatrician. When you go to the pediatrician, anytime, or a doctor, as you're growing, they always talk to you about your percentile rank, or your parents, right? So when a baby is born, like my son was huge. He was 10 pounds when he was born. And he was in the 98th percentile for weight because he weighed more than 98% of newborn babies. He was in like the 95th percentile for length because he was almost 2 feet long. So he was a really tall baby as well. So he was in the 95th percentile for length as well. Whereas our good friends had babies, preemies that were 4 months early. Okay, and their twin daughters were born way too early. So they were each about 3 pounds. So they were in probably the 5th percentile because they were only bigger. They only weighed more than 5% of their peers. Okay. So when you're talking about a percentile, one of the key factors is you have to have everything in order. Your data set needs to be in order. So here's a stem plot, which is nice because it's put everything in order already. So what you want to do to find the percentile for the following teams, the Minnesota Twins, who won 66 games, you're going to locate the Minnesota Twins. I told you in the directions, 30 baseball teams, right? So you're going to find number 66, and it's how many percent of your observations are less than it. So what we want to do is your percentile is actually your number of teams that are less than X. It's your number of data points less than you, not including you. All right. And then you're going to divide it by the total number of teams. So for data point 66, the Minnesota Twins, there are only 1, 2, 3 teams less than it, which is why I did 3 divided by 30, which would put them at the 10th percentile. The language is important. You're not in a percentile. The College Board is really particular, and statistics is particular that you're at a percentile. You're going to round to the nearest integer, and depending on like what your data set is. If your data set is a sample or a really enormous sample, or perhaps a population like babies born, right? The population of all babies born, then there really doesn't exist a 100th percentile. So like the number one student in your class can't rank above themselves. So the number one student is at the 99th percentile. Students who get 1600 perfect on their SAT score, they're at the 99th percentile. They're not at the 100th percentile because them and all of the other people who got a perfect 1600, you only count up the people who are less than them for the numerator, not including them. So, for instance, the Washington Nationals won 98 games. Here's 98. They're team 30 out of 30, but there are 29 teams lower than them. And that 29 teams lower than them puts them at the 97th percentile. They're not at the 99th percentile because there are only 30 teams. There's not 100 teams. Okay, so there's not every single percentile is going to be accounted for. There's going to be increments. Both the Texas Rangers and the Baltimore Orioles won 93 games. So when that happens, if there's two, you pick the smaller, okay, or the left one. They're the same number, so it's not smaller. Smaller was the wrong word. But you want to pick the one that's lower on the writing, like when you write them in order. You don't want to pick the higher one when you write them in order. You want to pick the leftmost one, okay? So there are 22 teams lower than this 3, which means that they're 22 divided by 30. They're at the 73rd percentile. Now, how we can use percentiles, if we go for a different example, if we take this, right, this is a table. It's a table in a cumulative relative frequency graph, right, that are going to show the distribution of median household incomes for the 50 states and the District of Columbia in a recent year. So there was one state that had a median income of 35,000 to 40,000. There were 10 states that had a median outcome of 40,000 to 45,000. We've talked about frequency Relative frequency is relative to the total. So 1 out of the 51 total, 10 out of the 51 total, 14 out of the 51 total. And these give us our percentages, just like we did with marginal and conditional distributions. Now we're going to add in cumulative as well. Cumulative is here. We have cumulatively during this class, there's only one. By the time we get to this class, it's here and here. It's this whole span. 1 plus 10 gives us 11. By the time we get to here, it's 1 plus 10 plus 14. So up to 50,000, starting at 35,000, up to 50,000 is 25. Your cumulative relative frequency is when you then divide it down to a decimal. All right. So what I've done is I first drew a cumulative relative frequency graph, and I did a bad job because I forgot to label before I copied this. So this here would be your median household income. This is your cumulative percentage of states, but this axis would be your median household income. Your first dot at 35,000 is going to be 0. This first dot is always going to start at 0 because by the time we get to 35,000, there has actually been no data points. All right, the smallest data point is there, but by the time you get to there, if you're approaching it, is 0. And then by the time you get to 40, that's where we're going to use these percentages to graph the rest of the dots. So this 1 or 100% is going to be at the 70,000. So 100% is here pairing up with the 70,000. Now you'll notice I have some dots drawn on mine this way. That's actually my work for as I do the next problem. Okay, so at what percentile is California with a median household income of $57,445? So I'm going to go to $57,000. I'm going to go dot, 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 dot up, and I'm going to go dot, 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 dot over. And that is how I get at approximately the 75th percentile. Because if you have a cumulative percentage, these are also your percentiles. Okay. Now, you can also work the other way. We want to estimate and interpret the first quartile of this distribution. So if we have the 25th percentile here, all right, the 25th percentile, 25%, I'm going to go over, find where they connect, and I'm going to go down, and it's going to be at approximately $45,000. All right. I would interpret that as 25% of states have a median income that is less than $45,000. Okay, you could also say it's the bottom 25% of states because quartile 1 is 25%. Quartile 2 is really your median, 50%. Quartile 3 would be 75%. So this number would be right at the third quartile as well. Okay, so what I want you to do is I want you to now try this problem. Okay, we're going to try problem 1 and problem 2. All right, and then your answers, you checked them as you did those multiple choice. Okay, so now let's talk about our second objective. All right, and our second objective is to apply the standard normal distribution to calculate percentages, z-scores, and data values. So the normal distribution is like it's our big kahuna. It's our big deal. It's the be all end all for stats. All right, we're going to spend a ridiculous amount of time on it this year. Today, we're just going to start with some baby steps. All right, your normal distribution is bell-shaped. All right, the mean is always going to be 0, and the standard deviation is going to be 1. The notation might be a capital N, and then in parentheses, you could have a 0 here, comma, a 1. All right. What we use this for, your standard normal distribution, is we can start by computing something called a z-score. A z-score is going to tell us how many standard deviations a data value is away from the mean. It can also be called a standardized score. So you need to be okay with it saying a z-score or it being called a standardized score. What the z-score does is it brings things that are on non-comparable scales down to all the same scale with a mean of 0 and a standard deviation of 1. So in real life, right, your best example, because you guys are living in it, right, are SATs and ACTs. The SATs are out of 1,600. The ACTs are out of 36. So how do you compare them, right? Well, you can figure out how many like standard deviations away from the mean each person gets. So if you get a 1,200 on the SATs and you get a 24 on the ACTs, well, you compare them to the average score and the standard deviation of those tests and then see if they're comparable or not. Here's your z-score formula. Z equals x, the data point, minus mu, the mean, divided by sigma, the standard deviation. Z equals 0 means you're exactly at the mean. If your z is less than 0, a negative z-score, that means you're lower than the mean. A z-score that's greater than 0 means you're above the mean. So what you're going to do, and how you'll see this show up in problems, okay, is it'll pop up here. Spider-Man took 2 tests. On which of these exams did he do better and why? So here's my z-score, right? I plugged in here, so test A, I had z equals x minus mu over sigma, and I got negative 0.5. On my B, I got z equals x minus mu over sigma, and I got negative 0.8. These are both negative, which means they're both lower than the mean. So if we come back to this number line concept, if here's the mean, negative 0.5 would be here, negative 0.8 would be here. On a test, the best are located up here. The worst tests are here. So the negative 0.5 is higher on the number line. So test A is the one they did better on because it has a higher relative position or a higher standardized score. Relative to the mean, the negative 0.5 is a better score. All right. So taking a look at the next example, Captain America took 2 midterms. He gave us his history test and his, which other one? History and science. So when you calculate on which test did he have a better relative position, it's on which test did he have a higher z-score, on which test did he do better. So your history, I've plugged it all in, I got 0.93, which means he's almost 1 standard deviation above the mean. Your science, z equals negative 2.75, means he's almost 3 entire standard deviations lower than the average. Okay, so if he did higher than the average on history and lower than the average on science, then clearly he did better on the history test. All right, so then what I want you guys to look at are these problems. Okay, so number 1, Lynette, a student in the class, is 65 inches tall. We want to find and interpret her z-score. All right, and another student in the class, Brent, is 74 inches tall. How tall is Brent compared with the rest of the class? All right, so is he really tall? Is he short? Is he, the top, right? And we would look at that. Okay. And then our 4th objective today. All right, we want to describe the effect of adding or subtracting, multiplying or dividing by a constant. We want to transform data sets. Okay, so the best example would be, let's talk about a test, because I know you guys have had teachers who have a certain number of points for a test or an assessment, and then in Genesis they change the point value, so they scale it, right? So if you have 30 test scores and the max score on the test was 50 points, okay, here's the distribution of test scores. All right, here's the mean. This is all your information from your 1 variable statistics. Now let's say that the teacher was super nice and just said, hey, everybody gets a +5. How would it change the shape, center, and spread? Well, let's look. Here's the original score. Here's the score +5. Notice the shape is the same exact shape. It just got bumped to the right. Okay. The spread is the same. They're still spread out the same. It just got bumped to the right. But the mean, look here, the original mean, new mean went up. Okay. So the average went up by 5. All of your measures of position, min up by 5, Q1 up by 5, median up by 5, up by 5, up by 5. Whoop, IQR stayed the same because our spread stayed the same. our range, our spread stayed the same. The other thing we can use to talk about spread is standard deviation. How spread out the data points didn't change. Adding 5 to everyone's score didn't change the spread. It just changed where they're located. It bumped them all to the right. Okay. Now, suppose that the teacher in the previous example wanted to go back to the originals, all right, and wants to make it out of 100 points. So because the test was out of 50, you want to turn it into 100, multiply by 2 to get it into 100 so that you can have your percentages. Now let's take a look at what happened to this graph, okay? So you have your original graph, you have your new, all right? Our sample size, all right, didn't actually multiply by 2. This is a mistake. Your sample size, there's still 30 dots, but your mean doubled. Your spread doubled. Your standard deviation doubled. Your 5-number summary, all of those things doubled. Your spread doubled for your IQR. It's double as wide. And your range is double as wide. Okay? So if you multiply or divide, everything stretches, multiplies, or shrinks, divides accordingly, except the shape. The shape is still the same. This is a left skew graph. This is still a left skew graph. It didn't reflect and become all of a sudden a right skew graph. It's still a left skew graph. All right. So I had written down here that in general, when you transform data, if you add or subtract a constant, it's going to add that number, A, to your measures of center and location. So your mean, your median, quartiles, percentiles. But it's not going to change your shape or your spread. Okay. That's the first example where I added 5. Whereas if you multiply or divide by a constant, it's going to multiply your center and your location. It's going to multiply your spread like it just did. It doubled our standard deviation. It doubled our IQR, but it doesn't change the shape. So when you're transforming data, you're multiplying or adding or subtracting or dividing, your shape is still going to remain constant. Okay. And then these down here are the appropriate book problems that are good to do in class.